Hello, in this section I'm going to look at the graphs of secant and cosecant. So basically one way to look at it is that you have two different types of functions. You have f of x equals to, let's say, secant of x, and then you also have g of x equals to cosecant of x. Now, one of the ways of which that we can approach this is that we just need to determine what are some restrictions to secant of x? Well, recall that there is a reciprocal function, or reciprocal identity, that says 1 over cosine of x is secant of x, provided that cosine of x is not equal to 0. Now, in any case, what that's telling you is that you're going to have two different functions where they're undefined respectively at some point. So cosine of x is equal to 0. Well, if you think about it, basically in the unit circle, it's undefined at, let's see, at pi over 2, and at 3 pi over 2, and then basically you can find more for every 2 pi. Um, so one way to look at this is that there's asymptotes, or you have that the points that are undefined are basically odd multiples of pi over 2. So basically, this is more or less the domain of our function. Now, there are other easy ways to do that, which I'll demonstrate it looking at the graph of cosecant. Now, this is what's going to be interesting. If we go ahead and we graph our cosecant function, or secant function, we're going to go ahead and do it in a way that it will look at the the cosine function first. So for instance, we have this is going to be 1 and this will be negative 1. Now we need basically that this is going to be pi over 2, and then we'll say that this is going to be pi, and then how about we go ahead and we extend this just a little. Okay, so this is going to be 2 pi, and then this is going to be 3 pi over 2. Okay, so we go ahead and plot our points. So we have 0, comma 1, pi over 2, 0, negative, or pi, comma negative 1, 3 pi over 2, comma 0, and then 2 pi, comma 1. Now, if we were to graph this equation, basically we would find that the graph of the equation would look something like this. Now, of course, this is like a really rough sketch of our graph, but if you graph it in the graphing calculator or even Desmos, you'll see that basically it's more or less the same thing. Now, we have that there are these points of where it's 0, but remember that there's no points that cosine of x cannot be, or there's those points that cosine of x cannot be 0. So this is kind of like the technique that we use to graphing cosine, secant and cosecant. Okay, so I look at the x-intercepts and I just basically say, well, from here, I just need to basically just reflect. So we're just going to reflect the graph like so and like so. Now, of course, we can do this also, like reflect it like that, and then reflect it like so. Now, this is actually the graph of cosecant, the blue lines. So if I kind of clean that up, for example, I'll notice that if I clean it up, like if I add, for example, another asymptote at negative pi over 2, because that's actually valid that we have a asymptote at negative pi over 2, and then I know that this is just going to be reflected. So in this case, this graph from negative pi over 2 to 3 pi over 2, that's acceptable, for instance. So in any case, like we can look at this and say that we can easily show or see that the range for this one is that you have minus infinity to negative 1 union from 1 to infinity. Now in this case, there technically is no amplitude, as there is no max, there is no min. So in that case, we just leave that alone. But we do know that the period still remains the same. The period is going to be 2 pi divided by b. Okay, so this is the graph of secant. Now, if you do want to clean that up, then you can just probably say, for example, we go to our Desmos graph and we just look at, for example, secant of x for when a is 1, b is 1. So let me see. I don't really want to see. Okay, no. Yeah, I don't want to see the reciprocal function. So in this case, we can see that this is the graph of secant. Now, if I change this, like if I change this from, let's say from negative pi to 2 pi, and then I change the range from, let's say like negative 2, and then we'll just do like, maybe like 2, or actually we can probably just say maybe like 3. Actually, yeah, let's do negative 3 to 3. So we see that our graph looks somewhat similar to what we drew over there. And if I do include the cosine function, I can see that this is where it's 0, that's where it's negative 1, and that's where it's 1. Then it comes back over here, and it's 0 again at 5 pi over 2. So there would be another asymptote right there. Okay, now I want to do the same thing with secant, or cosecant. And sorry that I confuse these. These are always like very closely, you can confuse them if you don't say co, or you can confuse them if you do say cosecant. So it's kind of weird. Okay, so we'll just go ahead and graph secant just so that you have it. So remember that secant has these asymptotes at negative pi over 2, and it has another asymptote at pi over 2. And then it has another one at pi over 3 pi over 2. So that would be pi, and then this would be 3 pi over 2. So okay, and then we have that this will be 1, and then this down over here is negative 1. So if we want to draw the graph of cosecant, we just have to draw it something like this. And then we have that it has its low over here, so it goes like that. And maybe I can make it a little wider. That way it kind of looks somewhat like the one over there. But in either case, like, we have that this will be roughly the sketch of our graph of secant. So here's our graph of y equals secant of x. Okay. Now, of course, if you did do more than one period, then you would just repeat the same process all over again. Now, let's look at, for example, how we can graph one of them. So, like, let's say that we have y equals to negative 2 secant of, let's say that we have pi x. Okay, so one way that we're going to have to look at this is that we can basically graph y equals -2 cosine of pi over x first. That way it makes more sense in terms of like how we can find the graph of secant. So for instance, the period is going to be 2 pi divided by pi, but that's equal to 2. So in that case, we have that this graph is going to be in phases of 4s, which means that it's moving by taking 2 divided by 4, which is a half. So basically that tells me that I can draw my graph in increments of a half using that 2 is the maximum and 2 is the minimum. However, notice that there's a negative, meaning that that kind of switches things up. Okay, so we just have to draw it respectively. So let's make this as our 1, and then, well, actually, let's make that a half. So we can make this a half, and then we'll make this 1, and then this is going to be 3 halves, and then this over here is going to be 2. Now, in either case, what we want to do here is just notate where 2 is. So let's just put 2 right there. Our scale is going to be a little funny, but I think it's okay. 1, 2, 3, so -2 will be down over here. Now, remember that basically the points on the graph, they're basically just getting reflected. So instead of having, like, for example, like a 2 down over here, -2, it's actually going to be +2 because it's going to be like way up there. So we have that one. But at 0, it's going to be -2. So we have that one. Now at 1/2, it's actually going to be just 0. So automatically I know that there's one right there. And there's another right there. And then I know that there's another right here. So all that I need to do is basically just connect the dots. So we can do that by just doing something like this. Okay, so next I just need to bring that down and then just connect this. Now from here, I just need to basically just find where it's 0 at, which basically we have that the equation is 0 right here at the 1/2. And then right there at the 1/2. Now note that in this case, it's going to be somewhat similar because we're just going to reflect the graph. So like we'll just reflect it like so. And then we'll just reflect it like so. And then we'll just reflect it over here. So we have that our graph is drawn as follows. So as we can see, basically the graph has a domain where basically the domain is such that the x value cannot be equal to multiples of a half, so odd multiples of a half. Okay, so that'll be 2n plus 1 times a half, and then this is what x cannot equal to. Okay, now in any case, like if you wanted to, you could probably add in, like that went like that, and that this reflects and it goes like that. That way you can complete the graph if you wanted to from that end, but it's all the same really. Now the range is the only thing that's different. You have that it's from -infinity, comma, -2, then union from 2 to infinity. So in this case, we still say that there is no max, there is no min, and that'll be it. So if we go back to like say for example the graph over here. So like say for example we change this to pi, and then we change this to -2. So the period is basically just 2, um, which if you kind of look at it like this, that you have that, um, yeah, so we have from 0, -2, and then from to 2, -2, and then over here as well. So it's kind of really difficult to see it, but like if we go ahead and we graph the reciprocal function, um, let me see. Mm, okay, actually, because I put a 2 here, that should be the same, so that's the only thing that's going to be different. Um, yeah, so like if you put an a here, there's your original function, I suppose. Usually it works out, like where we can just put an a there. Um, Actually, it's like this. Yeah, so basically you got to put the a, probably like that. No. Well, let's just put a 2 or 4, so that way it works out. Yeah, so we can make the snip scissor cutting method, uh, so we can make it work basically. Okay. Um, it's kind of weird because sometimes it does work out, but I just realized that yeah, you got to change up the values just in case. So try not to get confused on that, but it doesn't really matter technically, because usually when we refer to this, we're just saying that the graph is at either 1 or -1 in either case. Like if we do this, if we do 1, because you can see that it's the same. And then over here, okay. Yeah, so try not to get confused when you're looking at the reciprocal functions, because technically the a should be up over there. Uh, but yeah, because we're flipping it. Okay, now looking at another function like cosecant, we would do it exactly the same way. So like if we have y equals to cosecant of x, this is the same thing as 1 over sine of x, for which sine of x cannot equal to 0. Now x cannot equal to 0 basically at 0, pi, 2 pi, and so on. So basically that tells us that it can't be any integer multiples of pi. So this is actually the domain. Okay, so we have that the domain is odd integer multiples of pi. But I said that, I wanted to do that in an easier way. So for instance, we graph our sine function, and let's say that this is pi over 2, this is pi, this is 3 pi over 2, and then this is 2 pi. Now let's go ahead and say that 1 is right there, and -1 is right there. So we know that it passes through the origin, it has a maximum at 1, it has a 0 at pi, it has a minimum at -1, and then a 0 at there, at 2 pi 0. So We draw our graph of sine, and okay, now it's the same exact thing. We just have to draw these asymptotes where it crosses the x-axis. So we have an asymptote at the x-axis, or y-axis, right here at pi, and then right here at 2 pi. Now here we just need to basically do the same exact method where we just reflect it. So we reflect and we get the same function, sort of like secant. So in this case, it's more or less the same thing. We have that the period is still 2 pi divided by b, and then the only thing that is a bit different with respect to sine is that the range is going to be from minus infinity to -1, union from 1 to infinity. Now, if I introduce a constant, that of course is going to change, like how you kind of look at it, but it's actually the same. The a is actually just a constant, so that's why they match up. But in the Desmos graph, it's basically twice the amount, or yeah, you just have to account for the reciprocal essentially. Okay, now let's see. Um, if we go ahead and we look at another example, one example that we can look at is, say for example that we want to graph y equals to 3 cosecant of, okay, so let's say that we have cosecant of 2x, and it's 3. But let's say that we have, let's make this a little more interesting. So we have plus 1. Now, in this case, I need to basically figure out many things. I need to look at the graph of 3 of sine of 2x. Okay, so if you're using the graphing calculator, the original graph is technically the 6, but again, it gets kind of weird if you think about it like that. Like if you look at the graphing calculator and how it defines it, technically to match it up, it has to be 6, but that's a little confusing. So let's just do it like this, plus 1. Okay, so the thing that I know about this equation is that the amplitude is 3. I know that the period is 2 pi divided by 2, which is equal to pi. Now in that case, that means that we're having like these phase shifts, or these shifts of pi over 4. So that kind of helps me in terms of like figuring that out. Now I also know that it's stretched by 3 units and it's up 1 unit. So in this case, this is actually telling me that when I look at my x and y axis, I need to basically uh, I need to draw it in a way that it accounts for the shift change. So that's going to be, yeah, we want to make it big enough. So let's do this. Okay, so let's use this one. Okay, so I know that the largest is going to be 4. So in this case, let me see, 2, 3, 4. I want 4 to be there, but let me see. Maybe we'll just do this. 1, 2, 3, and then yeah, we'll just put 4 right there. And then -1, -2, -3, and then -4. But we don't actually technically need it that far down. but it's okay. Now we have that the period is pi. So here's pi over 4. Here's pi over 2. Um, let's see. And then here's 3 pi over 4. And then here is pi. Now, if you're wondering why am I only graphing just up to pi, it's because the period is pi, and basically you have that there's a compression. So you have that this graph represents that compression or will represent that compression. So this is the x, that's the origin, and this is the y axis. Now, I have that basically that this is shifted by 1 unit in terms of like the 1 unit, the plus one. So I know that the x-axis is technically being shifted up by 1 unit. So here, I just need to say that I know that I know that the graph is going to pass through 0, comma 1. At pi over 4, this is the one where it would be at 3, but plus 1, it's going to be 4. Um, So we have that it's going to be at 4. At pi over 2, that's where it's going to be 0, but it's going to be, what is that? Mm, yeah, this is where it's going to cross the y equals to 1. So right here, we're going to go ahead and say that the next phase shift is at 3 pi over 4, which will be minus 3, so that'll actually be minus 2. Then from there, um, yeah, because 1 minus 3 is minus 2. Then from there, it's going to close right over here. Now, if we look at this graph, basically we have that this graph says that the sine function, it looks something like this. Okay. Now, from here, all that we need to do is just figure out, like, for example, where are the asymptotes at? So, to find where the asymptotes are at, basically you're just going to have to look at where it crosses, let's see, where it crosses at y equals to 1. So where it crosses at y equals to 1, that's actually where you're going to have these asymptotes for that equation. Now it gets kind of difficult because you might say, but isn't it supposed to be the x-axis? Not necessarily, because like again, what was the original function? The original function was y equals 3 cosecant of 2x plus 1. If you kind of think about it like this, like if you say that you end up with 3 over sine of 2x plus 1, it's essentially just going to be more or less the same thing where you're just setting it equal to 0 and you're just trying to find where was the original function equal to 0 at, and then go from there. So it would be more or less the same thing, that it's going to be undefined uh, at the 0, pi over 2, um, and so on, and also at pi. Okay, if that doesn't make sense, then just set 2x equal to 0, pi, 2 pi, and so on, and that way you can get the asymptotes. Okay, but in my case, I'm just going to draw these right here, and I'm going to draw another one right there. And then I'm going to draw another one right here. Now, my graph has to reflect, so it has to reflect like this, and then it has to reflect down over here. Now, what you're going to say about this graph is that the range of it is from minus infinity to -2, and then that's going to be union from 4 to infinity, and then that's it. So if we actually go back, because this graph might look a little messy, for example, if we actually go back, to the graphing calculator, we can actually just type that in where, let's see, so this was going to be 2, and this was going to be 3. Now, in this case, let's see, the low point right here is at pi 4 over 3. Oh, yeah, we have to do +1, right? Yeah. So we have that the low point is at pi 4 comma 4. So if we look at that, that's pi 4 comma 4. And then if we look at the other low point, we have that should be 3 pi over 4 comma -2, which it is. Now notice that this is just one single period right here. And if you want, you can actually put a 6 right there. 6. Let's see if that works. Actually, it'd be 3. Mm, okay, so for this one, let's see. Mm, yeah, it's probably just better not to get too caught up on like the reciprocal, because we want it to basically be able to reach. We want it to be able to reach that amount. So that's probably why. Yeah, because we have that the function has to be able to reach to the to the reciprocal of it. But because our technique is somewhat different, that's why like the constant's not coming out correct. Like how to reach it. um, and it's just the way that I defined it basically. um, okay, but in any case, like you don't really have to worry about it too much. Um, yeah, because I don't really need that. Because yeah, if we do go ahead and like say, for example, like make that a 1, and then make this a 1, and then we change that to a 0, then they do kind of like overlap right here, right there, right there. Um, but I really wouldn't, to be honest, I wouldn't really worry about it too much that it's not matching up using the calculator. But we know that using the drawing, it does match up when we're looking at it like this. Okay, now, um, if I wanted to, I could probably change the axes if I wanted to. Now, the only reason that I might change the axes is just so that it looks a lot nicer. So if you really want to tweak with your graphing methods, you can actually say that this is y equals to 1. And then from there, just say, like, for example, that you have that's going to be pi over 4, and then that's going to be pi over 2, and then that's going to be 3 pi over 4, and then that's going to be 2 pi. From there, you would say that, for example, that this is going to be 2, and that's going to be 3, and that's going to be 4. And then you have that this is going to be -1, -2, -3. and then you have that this will be down over here, -4. So in that case, like you're just drawing essentially the same exact thing, sort of, that you have that this is going to be that point, that's going to be at this point, because 3 plus 1 is 4. That's going to come back down, and then that's going to come down to -2. Um, yeah, that should be a... Oh, okay, this should be... Our axis is a little bit off. Yeah. Okay. This will be 0. That's -1, -2. That's -3. Okay, so in that case, the next point is 3 pi over 4, which is -2. And then, yeah, that it goes to 0. From here, it should be clear that, that you're going to go ahead and go like this. And then you're going to come back up, or come back down, and go like that. Then from there, you're just going to basically kind of do like the scissor cut method, where you just reflect it. So in that case, like you just reflect it like so, like this. And then you just reflect it like so too. Okay. Now, one of the last things that, I'd want to consider. So, like, what if we had that one of our questions would be like to look at the transformations. So, if you looked at some of the transformations of your cosecant secant graphs, it's more or less the exact same thing. Because, for instance, if we look at an equation like y equals a times secant of b times x minus c and then plus d, it's more or less the same thing that we have that what is a doing, what is b doing, what is c doing, what is d doing. So in any case, like we can look at either of the two equations. I'm gonna look at probably just one of them. So when you're looking at these transformations, try to think of like in what way can you get their graph, which the easiest method is to actually look at their reciprocal function. But what gets again confusing is the a part. But if you try to ignore it and just try to graph it how you normally would, then it should work itself out. So like if you have y equals to, let's say, secant of x minus pi over 2, and then you have maybe like just, yeah, secant of x minus pi over 2. Then for this graph, we know that basically we know that we would essentially be looking at the cosine of x minus pi over 2 graph for that. So what we can do is look at, let me see, we can look at y equals to cosine of x minus pi over 2. So all that I need to do from here is just figure out like what's going on. Well, I know that the graph has been shifted by pi over 2 units. So we know that the new starting point is at pi over 2 and that the new endpoint is at 5 pi over 2. The way that I got that easily was I just thought, well, this thing moves in phase shifts of pi over 2 because I know that the period, okay, so the period is still just 2 pi, so 2 pi. But if you take 2 pi, you divide that by 4, that's going to be pi over 2, of which is the shifts. So in that case, that means that you move over another pi half, or pi half units. So you have pi, and then you have another one at 3 pi over 2. But then you have another one which completes the period of, let's see, well, Yeah, you have another one which will be 2 pi, and then yeah, you have one more. Okay, so 5 pi over 2. Okay, now you have that the maximum is at 1 and the minimum is at -1. So in that case, you would have that the graph of it looks something like this. It passes through, well, it passes through here because it would get shifted by pi half units. And then you have that that minimum is down over here. That's going to pass through there, and then that's going to pass through there. So all that we need to do is just draw our graph in a way that connects these dots. So we have something like this. Okay. Now the key is that you really need to just mark wherever it's going to be 0. So we have something like this. Now the rest of it is really just figuring out where else that you might have an asymptote at. Now, you're actually going to have an asymptote also at 0. So I'm just going to do this. So here we have that if we reflect the graph using, let's use orange. Okay, so all that we need to do is reflect the graph. So we can just do something like this. And we'll do something like that. And then maybe we can do something like this too. That way you can kind of see that the graph goes like that also. But the main thing from here is that we recognize that the period is still just 2 pi, but that the range, okay, now the range didn't really change by much, but it was minus infinity to -1, union from 1 to infinity, and then that was it. Now, of course, the challenge would be probably the graph to uh, getting the graph to look well, to reflect some of the changes, like if you were going to shift up by 1 unit or if you were going to stretch it by 2 units. So in that case, like for instance, we drew the graph of, let's see, cosecant. Okay, so this is going to be pi over 2. And then that should be it, really. Yeah. Okay. Um, Let me see if this is correct. Oh, wait. Yeah. Actually, our graph is defined a little differently. Um, yeah. This is off by some... Okay, so yeah, we have to change our definition of our graph. Let's go ahead and just write secant of x minus pi over 2. And then we'll just kind of close it right there. That way we have our graph. And then we can probably just change this into cosine of x minus pi over 2. And then we'll just close that. Now, one strange thing about that graph that I just drew is that it looks exactly like sine. And that's actually no coincidence that this looks like sine, because check this out. If I complete the graph, the original graph, the reciprocal graph, see like how it comes out like that? And then over here, we have that it completes like that. And then over here, we could have that it completes like so. And then, actually, let's see, that would be distributed over 2. So yeah, that would be like that. Okay, we'll just do like that. Okay, so one thing that you have to consider is why exactly would this kind of graph be the same as the sine graph? more or less, why would it be the same as cosecant? And the answer is actually because they're co-functions of each other. So that's one thing that's kind of interesting. When we move into the next section, we're going to look at some expansions of formulas. But in either case, I can always just leave you with that same exact question. Like, why is why is secant of x equal to cosecant of not no, 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 secant of secant of x minus pi over 2, why is that equal to cosecant of x? And the answer is that basically that they're co-functions of each other. But once we get into the next section, we'll look at some transformations, for instance. Okay, now what I'm going to leave you to is to try to find the graph of y equals to negative 2 cosecant of 3x um, minus pi, and then plus, let's say, 1. Okay, so you want to try this graph, okay? And really the hint is that basically what you just need to do for an example like this is just look at y equals to negative 2 sine of 3x minus pi and then plus 1, and you should get relatively the same thing like we did for the previous graphs. The only thing is that it gets a little tricky in terms of like how do we make sure that they do overlap each other. But as long as you kind of figure out like where sine of 3x minus pi equals to 0, then you can just apply the appropriate transformations if you just want to do it like that. In either case, it gives you the same thing because, yeah, if you think of it like this, like you just reflect it by 2 units, or reflect it over the x-axis, stretch it by 2 units. Now, there is a horizontal compression, but there's also a horizontal translation, not to mention the vertical translation. So be sure that you are aware of these different types of transformations that's going to be applied as needed, especially for when you're given a question like this, like on your exam.